Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the early 1600s, Johannes Kepler gazed at Mars through primitive telescopes and made observations that would forever change humanity's understanding of planetary motion. What he discovered were three fundamental laws that govern how every planet, asteroid and comet moves through space. These laws didn't just explain the dance of celestial bodies, they revealed the invisible threads that hold our solar system together. Kepler's first law states that planets orbit the Sun in elliptical paths, not perfect circles as previously believed. An ellipse has two focal points, and our Sun sits at one of these foci. This means every planet's distance from the Sun constantly changes as it travels along its orbital path. Earth, for instance, ranges from approximately 91.4 million miles at its closest approach in early January to 94.5 million miles at its farthest point in early July. The second law, often called the law of equal areas, describes how planetary speed varies throughout an orbit. When a planet moves closer to the Sun, it accelerates. When it travels farther away, it slows down. Specifically, an imaginary line connecting a planet to the Sun sweeps out equal areas in equal time periods. This elegant relationship means Earth moves fastest during Northern Hemisphere winter and slowest during summer. Kepler's third law establishes a precise mathematical relationship between a planet's orbital period and its average distance from the Sun. The square of the orbital period is proportional to the cube of the semi-major axis. This law allows astronomers to calculate orbital characteristics across the entire solar system and beyond, extending to exoplanets orbiting distant stars. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. These three laws represent more than mathematical curiosities. They describe the fundamental architecture of gravitational systems. Every satellite launched by NASA, every space probe sent to explore the outer planets, and every calculation predicting asteroid trajectories relies on Kepler's insights. The European Space Agency's recent Jupiter Icy Moons Explorer mission, launched in 2023, follows trajectories calculated using these 400-year-old principles. But what would happen if these laws suddenly stopped working? What if overnight, planets began changing their orbits randomly? The implications would extend far beyond astronomical curiosity. Our entire understanding of physics, from Newton's law of universal gravitation to Einstein's theory of general relativity, builds upon Kepler's foundation. These laws don't exist in isolation. They emerge from the deeper reality of how mass and energy warp the fabric of space-time itself. Consider the delicate balance maintaining Earth's habitability. Our planet orbits at an average distance of 93 million miles from the Sun, within what astronomers call the habitable zone, or Goldilocks zone. This distance allows liquid water to exist on the surface, not too hot like Venus at 67 million miles, not too cold like Mars at 142 million miles. The elliptical nature of Earth's orbit, with an eccentricity of just 0.017, ensures relatively stable temperatures throughout the year. The gravitational dance between planets also creates long-term stability. Jupiter, with its immense mass equal to 2.5 times all other planets combined, acts as a cosmic vacuum cleaner, capturing or deflecting potentially dangerous asteroids and comets before they can threaten Earth. This protective role depends entirely on Jupiter maintaining its current orbit at an average distance of 484 million miles from the Sun. As we embark on this exploration of orbital mechanics and cosmic catastrophe, we'll discover how the seemingly abstract mathematics of Kepler's laws translates into the very real physics that keeps our world spinning safely through space. The question isn't whether these laws could change, it's what the consequences would be if they did. The intricate choreography of planetary motion depends on a delicate balance between two fundamental forces: gravity pulling inward and momentum carrying objects forward. This cosmic tug-of-war creates the stable elliptical orbits that Kepler observed But understanding why requires diving deeper into the mechanics of gravitational systems. Newton's law of universal gravitation explains the force behind Kepler's laws. Every object with mass attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. For Earth orbiting the Sun, this gravitational force provides the centripetal acceleration necessary to maintain a curved path through space. Without this constant inward pull, Earth would fly off in a straight line at approximately 67,000 miles per hour. The concept of orbital velocity becomes crucial when considering planetary stability. Each planet must travel at precisely the right speed to maintain its orbit. Too slow, and it spirals inward toward the Sun. Too fast, and it escapes to interstellar space. Earth's orbital velocity varies from 65,000 miles per hour, catastrophic, its farthest point from the Sun, to 67,000 miles per hour at perihelion, its closest approach. This variation follows directly from Kepler's second law and the conservation of angular momentum. Angular momentum, the rotational equivalent of linear momentum, remains constant for objects in orbit unless acted upon by external forces. This conservation principle explains why planets speed up when closer to the Sun and slow down when farther away. Like a figure skater spinning faster when pulling in their arms, planets must increase their orbital velocity as their distance from the Sun decreases. The gravitational influence extends beyond simple two-body systems. In reality, every planet experiences gravitational tugs from every other planet, creating what astronomers call perturbations. These interactions can be calculated using celestial mechanics, a branch of physics that emerged from Kepler's work. The planet Neptune was actually discovered in 1846 through such calculations, when astronomers noticed unexplained perturbations in Uranus's orbit and predicted where an undiscovered planet must be located. Orbital resonances add another layer of complexity to planetary stability. These occur when the orbital periods of two bodies form simple numerical ratios, creating reinforcing gravitational interactions. Jupiter's moons, Io, Europa, and Ganymede, exist in a 4:2:1 resonance, meaning Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede. These resonances can either stabilize orbits or, in some cases, destabilize them over long time periods. The Hill sphere concept defines the region around each planet where its gravity dominates over the Sun's influence. Earth's Hill sphere extends approximately 930,000 miles in all directions, explaining why the Moon, at an average distance of 238,000 miles, remains bound to Earth rather than being captured by the Sun. Understanding Hill spheres becomes essential when considering how orbital changes might affect planetary satellite systems. Tidal forces represent another crucial factor in orbital mechanics. The same gravitational gradients that cause ocean tides on Earth also affect planetary orbits over geological timescales. The Moon gradually spirals away from Earth at approximately 1.5 inches per year due to tidal interactions, demonstrating that even stable orbits evolve slowly over time. Computer simulations of planetary motion, such as those conducted at the Jet Propulsion Laboratory, must account for all these factors simultaneously. These calculations track hundreds of variables across millions of years, revealing the long-term evolution of the solar system. Such simulations show that while planetary orbits appear stable on human timescales, they exhibit chaotic behavior over periods of millions to billions of years. The remarkable stability we observe results from billions of years of gravitational evolution. Planets that couldn't maintain stable orbits either crashed into the Sun, were ejected from the solar system, or collided with other bodies long ago. What remains represents a gravitationally mature system where each planet occupies a sustainable orbital niche. This understanding of orbital mechanics sets the stage for exploring what would happen if these carefully balanced systems suddenly changed, disrupting billions of years of gravitational evolution in a single night. At precisely midnight Greenwich Mean Time, something unprecedented occurs across the solar system. Every planet, asteroid, and comet suddenly shifts to a new orbital path, defying 4 billion years of gravitational evolution. The changes aren't gradual. They happen instantaneously, as if some cosmic force has rewritten the fundamental laws of physics. Within the first 24 hours, the consequences begin cascading through every aspect of Earth's systems. The first sign of change appears in Earth's rotation. Our planet's 24-hour day depends on the delicate balance between rotational momentum and tidal forces from the Moon and Sun. If Earth suddenly finds itself in a more elliptical orbit, stretching from 70 million miles at perihelion to 120 million miles at aphelion, the varying gravitational forces begin affecting rotational stability. The planet starts experiencing irregular day lengths, with some days lasting 23 hours and others extending to 25 hours. Satellite systems fail within the first 6 hours. The Global Positioning System, consisting of 31 satellites orbiting at an altitude of 12,500 miles, relies on precise timing and orbital mechanics to provide accurate location data. When Earth's gravitational field fluctuates due to the orbital change, satellite orbits decay unpredictably. The International Space Station, orbiting at just 250 miles altitude, faces immediate danger as atmospheric drag calculations become meaningless in the new gravitational environment. Ocean tides transform into chaotic phenomena. Normally, Earth experiences 2 high tides and 2 low tides daily due to the Moon's gravitational pull and Earth's rotation. If the Moon's orbit changes from its current nearly circular path to a highly elliptical one, ranging from 150,000 miles to 400,000 miles from Earth, tidal forces become wildly unpredictable. Coastal cities experience tide variations of 50 feet or more, flooding low-lying areas during extreme high tides and leaving harbors dry during extreme low tides. The most immediate threat comes from seismic activity. Earth's crust has spent billions of years adjusting to consistent tidal stresses from the Moon and Sun. Sudden changes in these gravitational forces trigger earthquake swarms along existing fault lines. The San Andreas Fault System experiences a magnitude 7.5 earthquake, while the Ring of Fire around the Pacific Ocean sees increased volcanic activity as magma chambers respond to altered stress patterns. Weather systems enter chaos. As atmospheric circulation patterns break down, Earth's weather depends on consistent solar heating patterns established by our stable orbit. When orbital changes alter the distance from the Sun throughout the year, atmospheric temperature gradients shift unpredictably. The jet stream, normally flowing in relatively stable patterns around the globe, begins meandering wildly. Hurricane-force winds develop over continental areas not accustomed to such weather extremes. Communications networks collapse as ionospheric conditions fluctuate. The ionosphere, a layer of electrically charged particles in the upper atmosphere, reflects radio waves and enables long-distance communication. Changes in solar radiation due to orbital variations cause the ionosphere to expand and contract unpredictably, disrupting radio communications, internet infrastructure, and emergency services coordination. Plant and animal behavior becomes erratic. As biological clocks, evolved over millions of years to match Earth's orbital cycles, no longer synchronize with environmental conditions. Migratory birds lose their navigational abilities as magnetic field fluctuations, caused by the orbital changes, disrupt their internal compasses. Flowering plants bloom out of season, disrupting food chains that depend on precise timing between pollinators and nectar sources. The financial markets crash within hours of the first observable effects. Modern economies depend on precise timing, global communications, and predictable transportation schedules. When satellites fail, communications break down and weather becomes chaotic. International trade grinds to a halt. The New York Stock Exchange suspends trading as computerized systems can't account for the unprecedented variability in global conditions. Most critically, the space debris environment becomes lethally dangerous. Earth's orbital space contains over 130 million pieces of debris larger than 1 millimeter. When gravitational conditions change suddenly, this debris begins moving in unpredictable patterns. The Kepler syndrome, a cascade of collisions creating exponentially more debris, begins as satellites and debris collide at altered velocities and trajectories. By the end of the first day, it becomes clear that the orbital changes represent more than an astronomical curiosity. They threaten the fundamental systems that support technological civilization. Emergency services struggle to coordinate responses as communication systems fail. Transportation networks break down, and natural disasters multiply. The immediate crisis sets the stage for even more profound long-term consequences as Earth's climate system begins responding to its altered relationship with the Sun. 7 days after the orbital shift, Earth's climate system begins revealing the full magnitude of the catastrophe. The planet's new, highly elliptical orbit carries it from 70 million miles from the Sun at perihelion to 120 million miles at aphelion, a variation that makes Earth's original orbit seem perfectly circular by comparison. This dramatic change in solar distance creates climate conditions unlike anything in Earth's 4.5 billion-year history. The most immediate climate impact comes from extreme seasonal variations in solar radiation. During perihelion, when Earth passes closest to the Sun, the planet receives approximately 3 times more solar energy than it did in its original orbit. Surface temperatures soar to an average of 130 degrees Fahrenheit globally, with equatorial regions reaching 170 degrees Fahrenheit. These temperatures exceed the heat tolerance of most plant species and make vast regions of the planet uninhabitable for human life. At aphelion, Earth receives only 1/9 the solar radiation it originally experienced. Global average temperatures plummet to -40 degrees Fahrenheit, with polar regions reaching -100 degrees Fahrenheit. These temperature swings occur over periods of just 6 months, far too rapid for ecosystems to adapt. The thermal stress fractures continental landmasses as repeated heating and cooling cycles cause massive expansion and contraction of rock formations. Atmospheric dynamics enter a state of permanent chaos. The extreme temperature variations create unprecedented pressure gradients that generate sustained wind speeds, exceeding 200 miles per hour across continental areas. The jet stream completely breaks down, replaced by chaotic circulation patterns that change daily. These superstorms carry enough energy to level entire cities and redistribute topsoil across thousands of miles. Water cycles become catastrophically disrupted. During the hot phase of the orbit, massive evaporation from oceans creates water vapor concentrations in the atmosphere 50 times higher than normal. This leads to deluges that dump 10 feet of rain in single storm events, causing flooding that persists for months. Conversely, during the cold phase, atmospheric water vapor condenses and falls as snow, creating ice sheets that advance hundreds of miles toward the equator within weeks. The ocean circulation system, which normally takes approximately 1,000 years to complete a full cycle, accelerates dramatically due to extreme temperature differences between hot and cold phases. Thermohaline circulation, the global conveyor belt of ocean currents driven by temperature and salinity differences, becomes a chaotic system, generating massive whirlpools and tsunamis. The Gulf Stream shuts down entirely, then restarts flowing, in reverse, carrying tropical heat to the Arctic while sending frigid water toward the Caribbean. Carbon cycle feedback loops amplify the climate catastrophe exponentially. During hot phases, permafrost across Siberia and northern Canada melts completely, releasing billions of tons of methane and carbon dioxide stored over millennia. Simultaneously, forest fires consuming entire continents release additional greenhouse gases. During cold phases, these gases condense or dissolve into the oceans, but the damage to atmospheric chemistry persists for decades. Agricultural systems collapse completely within the first growing season. Crops evolve to match Earth's original 24-hour day-night cycle, and seasonal patterns cannot adapt to the new 6-month extremes. Wheat, corn, and rice, the staple crops supporting most of human civilization, require specific temperature ranges and photoperiods that no longer exist anywhere on Earth. Even greenhouse agriculture becomes impossible as the extreme weather destroys infrastructure faster than it can be rebuilt. Ocean chemistry undergoes radical changes as pH levels fluctuate wildly. During hot phases, increased evaporation concentrates dissolved minerals, making seawater more alkaline. During cold Phases. Atmospheric carbon dioxide dissolves readily into the cold ocean water, creating carbonic acid that makes seawater extremely acidic. These pH swings kill marine ecosystems adapted to stable chemical conditions, causing the collapse of fisheries that feed billions of people. The cryosphere, Earth's frozen water systems, enters a cycle of complete destruction and reformation every orbital period. During hot phases, all glacial ice melts, raising sea levels by approximately 200 feet and flooding coastal areas where most of human population lives. During cold phases, this water refreezes into continental ice sheets, causing sea levels to drop and leaving former coastal cities stranded hundreds of miles inland. Atmospheric escape begins occurring during the extreme hot phases. When surface temperatures exceed the boiling point of water across large areas, water vapor rises high into the atmosphere, where ultraviolet radiation from the nearby sun breaks it apart into hydrogen and oxygen. The hydrogen, being light, escapes to space, while the oxygen combines with surface materials through oxidation reactions. Over multiple orbital cycles, Earth begins losing its atmosphere and water to space. Most devastatingly, the biosphere enters mass extinction. Species that survived previous mass extinctions, including the asteroid impact 66 million years ago that killed the dinosaurs, cannot adapt to climate changes occurring over months rather than millennia. Coral reefs bleach and die during the first hot phase. Tropical rainforests burn completely, releasing carbon stored over millions of years. Arctic species have no time to migrate, as their habitats disappear in weeks rather than centuries. The climate system's response to orbital changes reveals how finely tuned Earth's habitability truly is, setting the stage for examining how these changes affect human civilization and technology. 3 months after the orbital catastrophe, human civilization faces a technological collapse unprecedented in recorded history. The infrastructure that supports 8 billion people, power grids, transportation networks, communication systems, and manufacturing capabilities proves completely inadequate for the extreme conditions created by Earth's chaotic new orbit. Every assumption underlying modern technology becomes obsolete overnight. Electrical power generation fails across multiple fronts simultaneously. Solar panels, designed for Earth's original solar flux of 1,368 watts per square meter, cannot handle the threefold increase during perihelion. Photovoltaic cells overheat, and their efficiency plummets to less than 5% of rated capacity. During aphelion, when solar radiation drops to 1/9 normal levels, solar installations produce virtually no power. Wind turbines face even worse conditions as sustained winds exceeding 200 miles per hour destroy rotor assemblies designed for maximum wind speeds of 90 miles per hour. Nuclear power plants, initially seeming more resilient to orbital changes, encounter unexpected challenges. The extreme temperature variations affect containment systems designed for stable environmental conditions. Cooling systems fail during hot phases when external temperatures exceed the operating parameters of heat exchangers. During cold phases, emergency cooling water systems freeze solid, creating potential safety hazards. Several plants must be shut down permanently, as seismic activity from tidal stress changes, damages reactor containment structures. Transportation infrastructure becomes completely non-functional. Airports close permanently as extreme weather conditions make flight impossible. Commercial aircraft cannot operate when atmospheric density varies by factors of 10 due to temperature extremes, and sustained high winds make takeoffs and landings lethally dangerous. Railway systems buckle during hot phases as steel rails expand beyond design tolerances, while during cold phases, the rails contract and fracture. Highway systems crater as repeated thermal expansion and contraction cycles destroy asphalt and concrete, creating impassable terrain. Satellite constellations experience cascade failures that leave Earth effectively isolated from space-based services. The constellation of Global Positioning System satellites, essential for navigation, precision agriculture, and timing synchronization, becomes unreliable as orbital mechanics calculations become meaningless. Communication satellites in geostationary orbit find themselves no longer stationary relative to Earth's surface as the planet's rotational dynamics change. The Starlink constellation, consisting of over 4,000 satellites, begins experiencing collision cascades as debris from failed satellites creates an increasingly dangerous orbital environment. Manufacturing systems collapse as supply chains spanning the globe become impossible to maintain. Modern factories depend on just-in-time delivery of components from dozens of countries, synchronized through satellite-based logistics systems. When satellites fail and transportation networks break down, manufacturing stops within weeks. Computer chip fabrication facilities, requiring extremely precise environmental controls, shut down as power grid instabilities make it impossible to maintain the clean room conditions necessary for semiconductor production. Water and sewage treatment. Facilities fail as extreme weather overwhelms infrastructure designed for Earth's original climate patterns. During hot phases, water treatment plants cannot cope with massive algae blooms that result from high temperatures and increased evaporation rates. During cold phases, treatment facilities freeze and their pipes burst, contaminating water supplies. Urban areas with populations in the millions find themselves without clean water or functioning sewage systems. Emergency response systems, designed for isolated disasters rather than global catastrophe, prove completely inadequate. The Federal Emergency Management Agency's disaster response protocols assume functioning communication networks, transportation systems, and regional support capabilities. When all these systems fail simultaneously across the entire planet, emergency response becomes impossible. Hospitals lose power, cannot receive supplies, and are overwhelmed by patients suffering from extreme weather exposure and infrastructure failures. Financial systems collapse as electronic infrastructure fails. Modern banking depends on satellite, communications, internet connectivity, and electrical power, all of which become unreliable or non-functional. Electronic payment systems stop working, forcing a return to physical currency and barter systems. Stock markets close permanently as the companies they represent lose the ability to operate in the new environment. International trade ceases as ports become unusable due to extreme tidal variations and shipping lanes become impassable. Agricultural machinery designed for Earth's original climate becomes useless. Tractors and harvesting equipment cannot operate in sustained high winds or extreme temperatures. Irrigation systems fail as water supplies become unpredictable and pumping stations lose power. Greenhouse agriculture, initially seen as a potential solution, proves impossible as greenhouse structures cannot withstand the extreme weather conditions, and maintaining controlled environments. It requires more energy than failing power grids can provide. Human communities begin reverting to pre-industrial survival strategies, but even these prove challenging in the new environment. Traditional agriculture cannot function when growing seasons become unpredictably extreme. Hunting becomes impossible as wildlife populations collapse due to habitat disruption. Foraging fails as plant communities cannot adapt to the rapid climate changes. The most sobering realization emerges that human civilization's technological complexity has created vulnerabilities rather than resilience. Systems designed for efficiency in stable conditions become fragile when those conditions change. The interconnectedness that made global civilization possible becomes a liability when failures cascade through all connected systems simultaneously. As technology fails and human response systems prove inadequate, attention turns to the broader consequences for life on Earth and what the future might hold for any survivors of this cosmic catastrophe. 6 months into the orbital catastrophe, Earth's biosphere experiences the most severe mass extinction event in the planet's 4.5 billion-year history. The Big Five mass extinctions of the past, including the asteroid impact that ended the dinosaurs 66 million years ago, pale in comparison to the ecological devastation wrought by rapidly changing orbital dynamics. Unlike previous extinctions that occurred over thousands or millions of years, this collapse happens over seasons, giving evolution no time to adapt. Photosynthesis, the foundation of virtually all life on Earth, breaks down under the extreme orbital conditions. During perihelion, When Earth receives triple its normal solar radiation, photosynthetic organisms face impossible challenges. The intense heat denatures proteins essential for photosynthesis, while excessive light energy creates reactive oxygen species that damage cellular structures faster than repair mechanisms can function. Chlorophyll molecules, evolved to capture energy from Earth's original solar flux, become overwhelmed and begin breaking down en masse. During aphelion, when solar radiation drops to 1/9 normal levels, photosynthesis nearly ceases entirely. Plants cannot generate enough energy to maintain basic cellular processes, much less grow or reproduce. The 6-month-long winter periods prove longer than any plant species can survive without photosynthesis. Even deciduous trees adapted to survive normal winter dormancy periods of 3 to 4 months exhaust their stored energy reserves and die. Primary productivity, the rate at which photosynthetic organisms convert solar energy into chemical energy, drops to less than 1% of pre-catastrophe levels. This collapse reverberates through every trophic level of Earth's ecosystems. Herbivores lose their food sources within the first hot season as grasslands burn and forests die. Carnivores follow as herbivore populations crash. Decomposer organisms face feast or famine cycles, as massive die-offs create enormous amounts of organic matter during extinction events, followed by periods with virtually no new input. Ocean ecosystems suffer even more dramatic collapses than terrestrial systems. Phytoplankton, microscopic marine plants that produce approximately 50% of Earth's oxygen, cannot survive the extreme temperature variations and pH fluctuations in seawater. When phytoplankton populations crash, they take with them the foundation of marine food webs. Zooplankton, which feed on phytoplankton, die off within weeks. Fish populations, already stressed by temperature extremes, lose their primary food source and face extinction across all major species. Coral reefs, often called the rainforests of the sea, experience complete bleaching events that kill the symbiotic algae essential for coral survival. The extreme temperature swings between hot and cold phases occur too rapidly for any coral species to adapt. Within a single year, coral reef ecosystems that took millions of years to develop become lifeless calcium carbonate skeletons. The collapse of coral reefs eliminates habitat for approximately 25% of all marine species. Pollination networks, essential for plant reproduction, disintegrate as extreme weather kills pollinating insects. Bees, butterflies, and other pollinators cannot survive the temperature extremes or find flowers during the chaotic growing seasons. Plants that depend on animal pollination, including most fruit and nut trees, cannot reproduce even if they survive the climate extremes. This creates the extinction debt, where surviving plants represent the last generation of their species. Migratory species face particular challenges as the environmental cues they rely on for navigation and timing no longer correlate with suitable habitat conditions. Birds that migrate based on day length find themselves arriving at destinations during lethal temperature extremes. Whales following traditional migration routes encounter ocean conditions completely different from those their navigation systems evolved to expect. Monarch butterflies, whose multi-generational migrations span thousands of miles, lose the environmental landmarks and seasonal timing that guide their journeys. Despite the overwhelming extinction pressure, some organisms begin showing signs of rapid evolutionary adaptation. Extremophile bacteria, which already survive in harsh environments, begin thriving in conditions that kill other life forms. Some bacterial populations show genetic changes within just a few generations, adapting to the extreme temperature fluctuations and altered atmospheric chemistry. These organisms provide clues about what types of life might survive the orbital catastrophe. Certain plant species demonstrate remarkable phenotypic plasticity, the ability to change their physical characteristics in response to environmental conditions without genetic changes. Some desert plants, already adapted to extreme conditions, survive by entering extended dormancy periods during the most severe climate phases. A few grass species show ability to complete entire life cycles during the brief moderate periods between extreme hot and cold phases. Genetic bottlenecks become severe as large populations of most species crash to tiny numbers of survivors. The genetic diversity that took millions of years to accumulate gets lost in single generations. Species that do survive often lose the genetic variation necessary for future adaptation, making them vulnerable to extinction in subsequent orbital cycles. Seed banks and spore repositories become crucial for species survival. Plants and fungi that produce dormant stages, capable of surviving extreme conditions, have better survival prospects than organisms requiring continuous active metabolism. Some tree species survive as dormant seeds, even when adult trees die, waiting for environmental conditions that may or may not return to favorable ranges. The ecological collapse reveals how interconnected Earth's biosphere truly is. The extinction of key species creates cascading effects that lead to the collapse of entire ecosystems. Food webs that took hundreds of millions of years to evolve unravel in months. The biosphere that emerges from this catastrophe, if any complex life survives at all, will be fundamentally different from the rich diversity that characterized Earth before the orbital change. This mass extinction sets the stage for examining whether human civilization, or any form of complex life, can survive in the long term under these radically altered orbital conditions. 5 years after the orbital catastrophe, Earth has transformed into a world unrecognizable from the planet that once supported thriving ecosystems and human civilization. The extreme elliptical orbit has stabilized into a predictable, if hostile, pattern, but the consequences continue reverberating through every aspect of the planet's systems. What emerges from this cosmic experiment offers profound insights into the fragility of habitability and the precise conditions necessary for complex life. The surviving human population has contracted to perhaps 1% of pre-catastrophe levels, concentrated in carefully selected underground facilities near geothermal energy sources. These communities, numbering in the hundreds rather than millions, represent humanity's attempt to outlast the orbital catastrophe through technology and preparation. Nuclear-powered underground cities in places like NORAD's Cheyenne Mountain Complex and similar facilities worldwide have become humanity's last strongholds. These survivor communities face the challenge of maintaining technological civilization with severely limited resources. 3D printing technology, powered by small nuclear reactors, allows fabrication of essential components from recycled materials. Hydroponic food production systems, sealed from the hostile surface environment, provide basic nutrition. However, the genetic diversity of both human populations and food crops has become dangerously low, creating long-term sustainability challenges that may prove insurmountable. Surface conditions have reached a new equilibrium that varies dramatically with orbital position. During perihelion passages, surface temperatures regularly exceed 150 degrees Fahrenheit globally, with equatorial regions reaching over 200 degrees Fahrenheit. Atmospheric pressure increases significantly as heat expands the atmosphere, but the air becomes toxic with volcanic gases released by increased tectonic activity. No complex life survives on the surface during these periods. At aphelion, surface, temperatures drop below -60 degrees Fahrenheit even at the equator, with polar regions reaching -150 degrees Fahrenheit. Most of Earth's water freezes solid, creating ice sheets that advance toward the equator. Atmospheric pressure drops as gases condense, creating a thin atmosphere similar to Mars. The brief periods between these extremes, lasting only weeks, provide windows when surface temperatures might theoretically support life, but the rapid transitions prevent any ecosystem establishment. The oceanic system has fundamentally changed character. During hot phases, massive evaporation creates an atmosphere with water vapor concentrations approaching those of Venus, leading to a runaway greenhouse effect that amplifies temperature extremes. During cold phases, the oceans partially freeze, with ice sheets extending from polar regions toward the equator. This freeze-thaw cycle redistributes ocean chemistry and eliminates the stable conditions necessary for marine ecosystems. Remarkably, some life persists in deep ocean hydrothermal vents, where geothermal energy provides stability independent of surface conditions. These ecosystems, based on chemosynthesis rather than photosynthesis, continue functioning despite the orbital catastrophe. Tube worms, sulfur-oxidizing bacteria, and other extremophile organisms maintain small pockets of biological activity thousands of feet below the ocean surface, representing Earth's primary remaining complex ecosystems. The atmospheric composition has shifted dramatically over 5 years of extreme orbital cycles. Volcanic outgassing during tidal stress periods has increased carbon dioxide, sulfur dioxide, and methane concentrations. During cold phases, some of these gases condense out of the atmosphere, but the overall trend shows increasing greenhouse gas concentrations that may eventually lead to a permanently hot climate regardless of orbital distance. Geological activity continues at levels far exceeding normal background rates. The constant gravitational stress changes from the extreme orbital variations maintain elevated earthquake and volcanic activity. New mountain ranges form as tectonic. Plates shift under varying tidal forces. The constant geological upheaval prevents any surface environment from remaining stable long enough for ecosystem recovery. Space debris from the initial satellite cascade failures continues to pose hazards for any future space-based recovery efforts. The debris cloud in low Earth orbit has become so dense that launching spacecraft through it has become essentially impossible. This effectively isolates Earth from any external assistance and prevents space-based solar power systems that might otherwise provide energy for survival communities. Long-term climate modeling suggests that Earth's new orbital pattern may represent a stable configuration that could persist for millions of years. The extreme elliptical orbit does not naturally decay back towards circular, meaning the hostile conditions could continue indefinitely. This raises questions about whether complex life could eventually re-evolve to match these conditions, or whether Earth has become permanently uninhabitable for anything beyond extremophile organisms. The orbital catastrophe provides crucial insights for astrobiology and the search for habitable exoplanets. Planetary habitability depends not just on being in the habitable zone around a star, but on maintaining stable orbital conditions over geological time periods. Many exoplanets discovered by the Kepler Space Telescope and other missions have highly elliptical orbits that might preclude long-term habitability despite being at appropriate distances from their stars. The experiment also demonstrates how planetary systems achieve stability through billions of years of gravitational evolution. The solar system's current configuration represents not just a random arrangement of planets, but a gravitationally mature system where unstable orbits have been eliminated through cosmic time. Disturbing this balance, even through seemingly minor changes, can have consequences that persist for geological ages. Perhaps most soberly, the catastrophe reveals how dependent complex life is on stable environmental conditions. The biosphere that took billions of years to evolve proved extremely fragile when faced with rapid environmental change. This has implications for understanding climate change, asteroid impacts, and other potential threats to Earth's habitability in our actual timeline. The cosmic whisper from this thought experiment speaks clearly. Planetary habitability is not just about distance from a star or having liquid water, but about maintaining the delicate stability that allows complex systems to evolve and persist across deep time. Earth's current orbit is not just our home, it's our lifeline to the stars.